You know what acids are. Some sour-tasting foods, like orange juice and vinegar, are weak acids. Strong acids, like hydrochloric acid, can definitely turn you into Swiss cheese if you swallow them. Acids contain positive hydrogen ions, and the more positive hydrogen ions there are, the stronger the acid.
Bases are also known as alkalines. Basic solutions have a lot of negative hydroxide ions. The more negative hydroxide ions, the stronger the base. When an acid's positive hydrogen ions meet a base's negative hydroxide ions, it's like fire meeting water. Poof! The energy gets neutralized. The acid and the base neutralize each other. So, when the right proportion of a base is mixed with an acid, the mixture is neither a base nor an acid.
So, when you mix a basic solution with an acidic solution, the mixture becomes neutral. When the solution becomes neutral, it has reached the equivalence point. Makes sense, right? At the equivalence point, the number of positive hydrogen ions equals the number of negative hydroxide ions, and therefore neutral.
When a base is added to an acid and the solution reaches the equivalence point, the acid's hydrogen ions combine with the base's hydroxide ions, forming water as a product. The reaction's balanced chemical equation will tell you the ratio of starting chemicals you need for the reaction to neutralize or reach the equivalence point. For example, this balanced equation says that 1 mole of sodium hydroxide, NaOH, reacts with 1 mole of hydrochloric acid, HCl, to produce 1 mole of water, H2O, and 1 mole of table salt, or NaCl. We can tell by looking at the equation that we need 1 mole of sodium hydroxide, the base, to react with the 1 mole of hydrochloric acid in order for the reaction to reach the equivalence point and neutralize.
Where are we leading with all this acid-base stuff? Titrations!
No, that's not a titration. A titration is yet another way to determine the concentration of a solution. All you have to do to find a concentration with a titration is add an unknown concentration to a known concentration until the mixture reaches the equivalence point. Then do an easy calculation and you have the concentration. For a demonstration, let's go to...
It's Cooking with Professor Rowley!
And once again, folks, Professor Rowley.
When we mix a basic solution with an acidic solution, we'll know that we've reached the equivalence point when the mixture becomes neutral. We use dyes known as acid-base indicators to figure out the equivalence point.
Acid-based indicators, ladies and gentlemen. You heard it here first. Okay.
The balanced chemical equation is my recipe. It says right here that we need to mix 1 mole of hydrochloric acid with each mole of sodium hydroxide if our recipe is going to turn out right. So here we have a sodium hydroxide solution of an unknown concentration.
Wow.
Let's see how much we need to neutralize all 25 milliliters of this 0.15 molar hydrochloric acid solution. The acid-base indicator, phenolthalein, is already in the flask.
Wow.
Now I'll pour in the hydrochloric acid. When I add the sodium hydroxide to the hydrochloric acid, the phenolphthalein will tell us when the the reaction has reached the equivalence point.
Okay.
When it hits the equivalence point, the phenolphthalein will turn pink.
Wow. Oh, now, see, this is amazing, ladies and gentlemen. See, what's happening here is that the solution is actually turning pink, and then it's disappearing. Now, I don't know how much more of this I can take. I mean, this is really exciting. There's the pink again. And now it's not pink anymore. And now it's pink, everybody! Yay, pink! Pink's winning! Now it's not pink anymore, ladies and gentlemen. Hey, now it's pink again! Yeah, pink! More pink! Pink, 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 pink! 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 Now it's not pink anymore, Professor.
The acid-base indicator has turned pink, so the reaction has reached the equivalence point. It's done.
Wow! All right, now I'll take mine on right. Hold the mayo.
How much sodium hydroxide did you need to neutralize the hydrochloric acid? The burette tells us we used exactly 35 milliliters of sodium hydroxide.
35 milliliters, ladies and gentlemen. Yeah.
Yes, and what do you suppose the concentration is of the 35 milliliters of the sodium hydroxide solution?
Well, I don't know. How would we find that out?
Well, let's do a titration calculation.
Yeah, let's do a titration calculation.
Okay, here's the problem. What is the concentration of an unknown NaOH solution if you need 35 milliliters of the NaOH solution to reach the equivalent point of 25 milliliters of a 0.150 molar hydrochloric acid solution?
Jeez, I don't even know where to start with this problem.
Well, think about what it is you're trying to find. Molarity, right? So, start with a balanced equation that represents the reaction, because it will tell you the proportions of reactants and products in the reaction. According to the equation, NaOH and HCl react in a 1-to-1 ratio. So, we can assume that the number of moles of NaOH will equal the number of moles of HCl. Now, think about the problem. We started with 250 milliliters, or 0.025 liters, of 0.150 molar hydrochloric acid. So, the concentration of this hydrochloric acid is 0.150 molar in 25 milliliters of solution. What concentration would our 0.035 liters of NaOH solution have to be in order for it to react in a 1-to-1 ratio with 0.025 liters of hydrochloric acid? Remember the formula for molarity? M equals the number of moles, N, divided by the number of liters, L. We can fill in the L because we know the volume of NaOH is 35 milliliters, or 0.035 liters. But we need to find N, the number of moles. The equation we'll use to find moles is just a rearrangement of the molarity formula. N, the number of moles, equals capital M, the molarity, times V, the volume in liters.
You're probably thinking, hey, we don't have enough information to figure out how many moles of NaOH we have. Don't worry. We do have enough information. It will just take a few steps to get there. First, check out the balanced equation. It shows NaOH and HCl in equal amounts. That means that the number of moles of NaOH you have will equal the number of moles of HCl. So, find out how many moles of HCl you've got, and you know how many moles of NaOH you've got.
We have enough information to find how many moles of HCl we have, so we can figure that out and apply our result to the NaOH. Convenient, huh? Here's the equation to find moles again. N, the number of moles, equals the molarity, capital M, times the volume in liters. Let's do the math. Our culinary chemists used 0.025 liters of 0.150 molar hydrochloric acid, or HCl. That's 0.150 molar solution times 0.025 liters. That equals 0.00375 moles of HCl. To make it easier to deal with, we'll write this figure using scientific notation. According to scientific notation, 0.00375 moles of HCl is the same as 3.75 times 10 to the negative 3 moles of HCl. Again, since they are equal in the balance equation, the number of moles of NaOH will equal the number of moles of HCl. So we need 3.75 times 10 to the negative 3 moles of NaOH.
Now we have enough info to find the concentration of the unknown NaOH solution. Use the molarity or concentration formula. Molarity equals the number of moles divided by the volume. In this case, that's 3.75 times 10 to the negative 3 moles divided by the volume, which we've also written using scientific notation. 3.50 times 10 to the negative 2 liters. Cancel it down to 3.75 moles over 3.50 liters times 10 to the negative 1. Our answer is 0.107. That means that 35 milliliters of NaOH solution reacting with 25 milliliters of 0.15 molar solution HCl must have a molar concentration or molarity of 0.107. Wow!